Is the voice is audible all of you?
Yes, sir.
Yes, sir.
Hello.
Yes, sir.
Okay. So for the experiment 5, 6, task 5 and 6, at least you have to use your common sense. That how we can able to represent the things. That is what you need to understand. Okay. For example, you know about the things, let's suppose, let me share the screen so that how you can able to represent it. Screen is visible, all of you?
Yes,
Screen
sir.
is visible?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
So okay, let us consider there is a definition of exposition. Like you have to explain the exposition. One or two students, the Deep and one more, I think the Jayesh had given how we can able to represent the things. What about the exposition you have? What actually you need to do if you don't have the laptop? Write some two-line definition about the exposition. Then draw a graph. Let's suppose this is your input you have, sinusoidal signal. After moving the exposition, what should be your output? Now the output will be like this. The same amplitude. What happens? This is the x position you had done the movement. You will move in the x direction. Let's suppose the y position. So in y position, what actually will do? You write the definition, two line. Then show the graph. You have this waveform. After moving the y position, what happens? The graph will move up direction. So this is nothing but a movement of a y position. What happens for a ground? How will represent? How will you tell that okay, if I press the ground button, what happens? Write a one or two line definition if you have these signals from a function generator. After the ground button, what should be output? This is what are the output. What is the big deal in this? Is it clear or not?
There will be straight lines.
This is a straight line, the zero DC line.
Yes.
What is the big deal in this? Those who have the laptop, they will do the multi-sim and they will put the screenshot. Those who don't have the laptop, these are the things you need to explain. What is the seventh task, sixth task? Explain the dual
Invert
oscilloscope.
the
Invert is
Yes,
a
sir.
means, okay. Invert, for the invert, let's suppose this is the graph you have. Wait. If you need the invert, what do you, when you press the invert button, this waveform will start from here. This is the invert. Then there is one task of the two oscilloscope, two functions in it. So draw a screen, take two waveforms. Let's suppose this is the first waveform and this is another waveform. Okay, extend the screen till here. Let's suppose this is the screen of an oscilloscope, for a dual channel oscilloscope. Measure the voltage, this one is, let's suppose, channel 1, this one is a channel 2. Measure the voltage and current, that's all. What is the big deal in this? If you don't have a laptop, do it with the pen and pencil. Yes, any other doubt? Is it clear, all of you?
Yes, sir.
Still have doubt,
yes
you can
sir.
ask right now. Yes?
Yes.
The voice is clear?
Yes, sir.
Hello?
Yes sir.
Okay. So who are the students have not been added in the canvas? Just write down the mail ID in the chat box. Okay, Ignesh. Anyone else? Purchase? Sit. Janil. Only this many students? Heat. Anyone else? After heat, anyone is there? Janvi. Okay, after Janvi, anyone? Jay. Those who are already added in the canvas, don't write the mail ID. Those who don't have the access, those students only should write. Okay, Kalpesh Chawda. Anyone else after Kalpesh? Sorry, Kalpana. Anyone after Kalpana? Maulik, you had joined recently? Maulik?
नो आइडिया सर मैंने अभी तक देखा नहीं है
Maulik.
यस सर मैंने अभी तक देखा
देखा नहीं है तो
यस
भाई
सर
देखना पहले इनबॉक्स में देख तो सही तू तेरे मेल आईडी में ये दो बार रिक्वेस्ट आएगी तो तू अपलोड किस में करेगा कौन सा मेल आईडी में करेगा अपलोड First, I had given the instruction, those who didn't get a request in the canvas, those students only write that and or mail ID. Out of these, how many students already didn't check the inbox? How many students have not checked the inbox till now? It will create a two profiles for you. Yagnesh, did you check it or not? Should I send you the request?
Yes, sir. I
Yagnesh,
checked. Yes, no inbox. मतलब कुछ मेल नहीं आया सर
हाँ,
अब तक इनविटेशन का.
ठीक है. Jayesh, for you, did you check it or not?
नहीं सर अभी नहीं आया इनविटेशन
ठीक है. हर्षित, or sit. Did you check your inbox?
नहीं आया है.
ठीक है. Janil
सर अभी
saw.
तक नहीं आया, मैंने चेक किया.
Janvi,
यस सर नहीं आया है.
did you check it the mail or not?
हाँ सर चेक किया है, नहीं आया है.
When you had joined the institute?
सर मंडे.
Okay. So this was your first lecture?
यस.
Okay. All of you check your inbox. All of them got the request in your inbox. Okay. Did you check it or not? Did you get the invitation?
सर मुझे मिल गया.
So all of you just
Yes,
I'm sharing you on screen. All the students just do the same thing. Those who already got the request, the same student I am asking. Just go to the first of all, open the canvas.
Hello, sir.
Yes.
I got the mail.
Okay. All of you students, those who got the mail and those who are afterwards getting the mail, they need to do these things. All the students. Go to the dashboard and go to the BW2020 menu. There you will find settings. Go to the settings. There you will find a profile. Sorry, my mistake. Go to the account and there you just go to the profile. And there you just go to the edit profile. You go to the profile and there you just go to the setting. And in setting, edit settings will be there. Click on the edit setting. Here, the full name, display name and the short name should be the same. The full name for you, all the students, write down your enrollment number. Let's suppose this is my enrollment number. Underscore your full name. Should I explain it again? Should I explain it again?
Yes, sir.
No sir.
Yes. Starting from here, click on this tab, go to the profile. In that profile, go to the settings. There you just click on the edit setting. All the names, full name, display name and the sort table name should be same. First your enrollment number, underscore, your full name. Don't write the first name and the last name. Write down the full name what you have been used for admission. Okay, the full name, copy this, paste it to the display name also and the sort name also. It should be same. And then update setting. Once you are done, let me know. Done, all of you?
Sir, can you explain it again one time, sir?
Where you are? Share your screen. Share your screen. Yes, go to the canvas. Open that. There will be, okay, open that. Now go to the, here you don't have the profile, go back then. Instead of home, there will be like profile options will be there in the mobile. Change it to the desktop. Change it to the desktop. View. View of this Chrome, change it to the desktop. ડેશબોર્ડ ની ઉપર હોય ને એના ઉપર ક્લિક કર. ઇટ્સ ઓકે. ડેશબોર્ડ ની ઉપર જો 3 લાઈન છે ને એમાં પ્રોફાઇલ જેવું છે કઈ સેટિંગ્સ માં જા. પ્રોફાઇલ સેટિંગ. હા ચેન્જ કરી નાખ્યા. એડિટ યુઝર નેમ માં enrollment number and then your underscore the full name.
एक्सक्यूज मी सर.
Yes.
सर मुझे अभी तक मेल नहीं मिला है.
Janil Shah.
यस सर.
Same Marwad University mail ID you are using.
यस सर.
You should get because you are added in the canvas. Refresh your. Hmm. जनील साहब रिक्वेस्ट पेंडिंग है सेंड हो गया.
सर
रिसेंड किया इनविटेशन जनील चेक कर. यस
जस्ट अ मिनट सर.
सर मैं गेट सर मेल पे गेट स्टार्टेड पे क्लिक कर रहा हूँ तो वो लॉगिन और पासवर्ड मांग रहा है.
गेट स्टार्टेड पे तूने जीमेल मारवाड़ यूनिवर्सिटी पे लॉगिन किया है पहले.
हाँ सर मारवाड़ यूनिवर्सिटी पे ही किया लेकिन फिर भी गलत बता रहा है.
शेयर कर स्क्रीन.
हाँ सर.
कल्पना did you get it or not? कल्पना hit.
No, sir, we are also not getting.
Sir.
They are asking Gmail address and password.
Yes, sir.
They are asking here email.
Okay, didn't get the Gmail and password? Open your Gmail where you had same username and password. Use that same Marwad University.
Sir, here email and username is there, but password what is it?
You need to set the password. पासवर्ड आपको सेट करना है.
Means
ये सेम पासवर्ड इसमें जो पासवर्ड है वही पे लिखो हुआ. हाँ इसमें जो पासवर्ड आपने यूज किया वो सेम पासवर्ड वहां पे. एक्सेप्ट करो आ गया.
Yes. Okay. All this.
Okay, anyone else?
Welcome. I have canvas.
Hmm. Okay. Yeah, you have it. You have it.
I have canvas account. Sir, now it is
No, go
asking
back.
for email and password.
Go back. Go back. Create an account. Set the password. That's all. Okay. Create my account. Just you need to write a password over there.
Okay.
Okay. Okay. Any other
Okay,
students? Are
sir.
you very good? Still you didn't get the mail. Wait.
Sir, still I can't
Sir.
receive the mail.
Jamil, I had resend it. Invitation I had resend you.
But
Vaibhav.
Sir.
Hmm.
I edited the setting. Can I show you for just a second? Is it correct or not?
Yeah, you send it. Vaibhav, you set on a mail ID?
Yeah, sir.
Vaibhav,
Yes, sir.
write down your mail ID. Yes, done. Correct. Ankur.
Okay,
Sir,
sir.
I sent my email ID in chat box.
Yes. It's Vaibhav Mawani. Correct?
Yes, sir.
Check now. Check your inbox. Maulik already sent. Still check invitation. I think the
No, sir, I don't receive.
both of you check again. Janil Shah. Janil Shah. Wait. Check Janil now.
yes, just a minute, sir.
Again. Vaibhav.
मुझे भी नहीं
Yes,
मिला
sir.
सर अभी तक.
मिल जाएगा कोई बात नहीं चलो अगर आज नहीं मिला तो नेक्स्ट लैब में तो मिल ही जाएगा ठीक है द फर्स्ट असाइनमेंट इज लाइक 15th डेट so I had sent all the re-invitations to all the students still if you didn't get we'll discuss in the next class or tomorrow's class so shall we start our lectures by today the topic is the PN diode I hope everyone is present in the last class our students are present in the last class okay so in the
Yes,
last
sir.
class yes we had teach about. So anyone just explain me, let's suppose, talk to the Meet Patel. Can you explain just what are the things we had discussed in the last class?
Hello, sir.
Yes,
Yes.
yes, sir. We discussed how to find the peak voltage, frequency, and time and all.
Okay. So let's suppose consider what is the difference between analog and the digital oscilloscope? Hello? Hello? Meet?
Yes, sir.
How you can able to measure it? What is the difference between analog and digital oscilloscope?
Sir, tomorrow I was not there in your lecture,
Hmm.
and tomorrow I was new for your lecture.
So those who are new for my lecture, see, tomorrow also like we are at introduction session that we had calculated the voltage and peak to peak. So we have recorded videos. But today I'm going to upload those videos. So you can directly use that links when you can able to find in your portal itself, okay? The link.
Sir,
So you can watch that video.
in
Hmm?
Canvas we have to write full name with father.
Just his father also. Okay. So that
Sir,
students can
how do
able to
we
understand.
Sir,
Yes.
how do we have to upload that like task 1 to task 6? I mean, I don't have laptop, so in PDF or photo format.
Take the photo, convert into a PDF, merge all the PDF and then upload it. Okay?
Okay,
Don't
sir.
upload one by one PDF. Okay? Is it clear? Any doubt you can ask right now. चलो પછી હું ચાલુ કરું. કોઈ પણ doubt હોય તો પૂછો પછી હું ચાલુ કરું.
સર તમારા પ્રીવિયસ લેક્ચર નું લિંક છે એ મતલબ
હા,
એપ
મળી
માં
જશે.
મળશે કે ક્રોમ માં જઈને
મારવાડી યુનિવર્સિટીની વેબસાઇટ ઉપર મળી જશે. મીન્સ હવે તમારી એપ્લિકેશન છે ને મારવાડીની લોગિનની, મળી જશે. ક્લિયર? ડન? Okay, so start now. No questions. So we'll start with the simple, the basic fundamentals and the PN diode, what we are have it. So let me share the screen so that you can able to understand about the PN diode. Okay. Is the screen is visible for you?
No, sir.
No, sir.
No, sir. Okay. Now?
No,
No,
sir.
sir. Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. So starting with the formation of the PN junction. Everyone knows if you separate this word PN, so this is nothing but a P type and then stands for a N type. So everyone knows about this thing. Semiconductors are mainly divided into how many types?
Sir, trivalent.
How many
and
types?
Pentavalent.
2 types. No, wrong.
Intrinsic and extrinsic?
Yes, the intrinsic and extrinsic, the 2 types. What happens in intrinsics? Do we have an extra electrons or extra holes? Do we have the extra electrons and the extra holes in intrinsic semiconductor?
No.
No, sir.
Then what we have? How many electrons we have in the outermost orbit?
4.
4. Okay, correct. What you say. So when the recombines with another silicon atom, it will be a 8. Okay. Okay, good. Now, what happens in the extrinsic semiconductor? This is what we understand about the things. That is the silicon atoms, the outermost orbit by covalent bond sharing. We have 8 electrons on the outermost orbit by K-ring sharing. Actually, its valence electrons is 4. If it is less than and more than 4, you know, its semiconductor converts into insulator and a conductor. Exactly 4, it's a semiconductor. Now, let's suppose if I want to make this intrinsic semiconductor as an extrinsic semiconductor. How many types of extrinsic semiconductors we have?
2 types.
Which are they?
N and
Trivalent
P.
and pentavalent.
N and P type. Okay, N and P type. Which are the impurities we'll add? We had remember like this. And another name is B. Another name is
Baggy.
this one is A. Okay. Where should I work? Which is the pentavalent impurities? Which are the pentavalent impurities?
Tab. PAB.
Okay, this is the pentavalent. So should I put it in the N type or a P type? Where should I put it?
N type.
N type, P type.
P type.
P type.
P type.
The pentavalent impurities have extra electron or holes?
Extra electrons.
Extra electron.
So extra electrons means if you have a millions of, if you have the millions of pentavalent impurities, what happens?
Millions of electron extra.
So where it should come, N type or P type?
N type.
N
N
type.
type.
Obviously the N type. Coming to this one, it's in the P type. What is the full form of this one? P stands for? P stands for?
Phosphorus.
Okay. A stands for?
Arsenic.
Okay.
Arsenic.
Arsenium.
Then another A.
Antimony. Anti.
And B stands for? B stands for?
Bismuth.
Bismuth.
Bismuth. What about this?
Boron.
Boron.
Aluminium.
Indium.
Good.
Helium,
Okay.
arsenic.
So this will comes under the category of P type. Good. Okay. This one is a P type. N type. Now same way, what we had seen, the N type semiconductor, previously the intrinsic, and if you want to convert N type extrinsic semiconductor, you will add with the pentavalent impurities, and there is nothing but a phosphorus, arsenic, antimony, and a bismuth. Good. Now, let's suppose if you want to convert your semiconductor into a P type, what you need to do? You need to implement the impurities as a trivalent impurities, boron, aluminum, gallium, and the indium. Okay, for this actual conversion of a P-type extrinsic semiconductor. Now, it's such a question comes into the mind, the person who is doing the research. We know that, okay, we can able to convert into N-type material and you know also convert into a P-type material. But what happens if we combines both of the materials together? So we have a P-type and N-types. When we combines together, it makes a diode. And that diode we call as a PN diode. It's clear all of you till here? The scientists got an idea that what happens when we combine this P and N diode together to work has some different formula. So we got something, a diode functionality, and that scientists gave the name as a PN diode. All the electronics gadgets, first electronics gadgets came in the market, electronics device came in the market as a PN diode only. What are the BJT laser diode, general diode, everything are nothing but applications of an PN diode. If you change the impurities, it converts into a laser. Again, if you change the impurities in the PN diode, it converts into a general diode. If you change the impurities in the PN diode, it may works as a photovoltaic cell. Means if you combine two back-to-back PN diode, it makes a BJT. So PN diode is a basic electronics device from which other device has been generated. So if you know at least the working principle of the PN diode, the rest of the things to be easy compared to other studies. Okay, now let us move to the point, a symbolic representation of the diode. Though we already studied in the 12th standard about the PN diode, here the p-type material and the n-type materials, when it combines together, it creates some space, and what this space we call a junction. A junction is nothing but a deflection region where it just combines p and n-type material, so it separates the p and n-type material. Okay, is it clear about the p-n junction diode?
Yes.
Okay.
Yes, sir.
Now if you look at the symbolic representation, it's a two-terminal device, a terminal number 1, a terminal number 2. If you have the two terminal, one should be positive, one other should be a negative. So at this terminal, this is positive and this is negative. How you would represent in a schematic symbol? Let's suppose if I have the diode symbol like this. Now this line indicates a negative terminal and the line we don't have it is under the positive terminal. If you look at the physical real component, the real component will be look like this. The line which have a gray color indicates is a negative terminal, and other terminal we have a positive terminal. This is a symbolic representation of a diode. This is how physical circuit, what we have, the representation of PN junction, a schematic symbol, and the real component look like this. Just have a look. Okay, now next. Understand nicely, the concept of the PN diode is very easy to understand. So we have the p-type, that is a majority charge carriers. What we have, the majority charge carriers in a p-type?
Holes.
Holes are majority. And which are they? The minority charge carriers? Electrons are a minority charge carriers. Now here we have the holes. That means it can able to accept the electrons? Yes or no?
Yes.
So here this holes, so let's suppose this one boron element have a one acceptor ions, it will accepting the electrons, so it's called as acceptor ions. Are you getting or not? Okay, after adding the boron to the silicon, it will create a one acceptors. If you add a millions of boron element in a silicon, what happens? It will accept, generates an acceptor about millions of acceptors. So we have a third, and that is what we call as a acceptors. Are you getting or not? Clear all of you?
Yes.
We have a majority as a whole, minority as an electron, and we also have acceptors. What happens over here? Look at over here. These are the electrons we have. So it donates the electron. That means he won't accept anything. He donates the electrons to the p-type region. So what happens? Here When you add a pentavalent impurity, let's suppose phosphorus. So what happens? During the addition of a phosphorus, it will generate millions of donor ions. Okay, that means we have the majority as electron, minority as a holes, and one more we call as a donor. Okay, these are the donors. Donor. Look at the slides till if anyone has a doubt, you can ask.
Sir,
Yes.
is that charge of the donor means positive?
Yes. To whom is donating? To whom is donating?
Okay, sir.
Okay. Acceptor means to whom it accept, to what is expecting. Electron is expecting, so negative. Clear?
Okay, sir. Yes.
That's why I put the slide in front of you. Still, if anyone has a doubt, you can. Okay. Now, let's suppose consider by default, whenever you connect your P and N diodes together, there is always be a narrow junction in between the P and diode. So this one is area for P type, this one is an N type. There will always be a one narrow junction. Wait, let me draw a straight screen, straight line. Okay, this is what we have called as a junction, which separates the P type and the N type material. Now what happens? During this P type and N type, here is phosphorus, so they each and every phosphorus have extra electrons. And here at this place we have boron, so each and every boron have one hole. That means the trivalent impurities in the P type and pentavalent impurities in N type. Is the thing is clear, all of you? Now, this free electron in a phosphorus has some amount of energy to break this junction. Are you clear or not? Free electron is so. What do you mean by free electrons? It has certain energy to move inside the crystal structure. Are you agree with that? Are you agree with that?
Yes.
So these free electrons have the energy to break this junction and combines with this electron, this hole. So what happens? After that situation, the electron from this place will move and it will occupy the space over here. Yes or no?
Yes.
Same things happens for another electron. This electron, this will move, this will move, this will comes over here, this will move. Now what happens? This phosphorus have how many electrons? Like here there will be one electron, okay? So there will be 8. So I can say that now it is in a stable state.
Yes.
Yes or no? So now this junction extend from here to here. Yes or no?
Yes, sir.
Yes.
So small junction. How these electrons get the energy? When you apply a positive charge over here, and the negative charge over here. When you apply external positive charge, what happens? Okay, now don't talk it about the positive, because otherwise we can confusion state. This is clear, all of you? Now the junction will be at this position. Now the junction at this position, because they have the stable states. Now what happens? After you apply a more negative voltage, so these electrons, external battery if you connect and if you get voltage over here, so what happens? This electron will get excited more and it will try to cross this junction and sit it over here. Are you getting or not?
Yes.
Yes.
So this electrons again it will jump and try to sit over here, here and here. So what should be the junction right now? Junction will be like this. Again, some energy, let's suppose after certain energy, now this junction will be the permanent region. Why? Because this electron now doesn't have that much of energy to break this and go and sit over here. Are you getting or not?
Yes, sir.
Okay, now these electrons cannot cross over this junction because now it's getting a thicker and thicker wall. So at one point, this junction will remain same when you don't apply any voltage. Okay, now I don't apply any voltage. What this is the state I am talking about when you are connecting your N-type and P-type together. So during the N-type and P-type, when you put it together, there will be a small junction which will be created due to this region. Any doubt? Look at the diagram. If you have any doubt, you can ask.
Sir, can you please once again explain permanent region? Actually, your voice is breaking. So,
What do you didn't understand?
sir, that from you are telling that like permanent region or something like that. So I actually can't hear due to voice breaking.
Okay. So when you don't apply any voltage and when you combine these two materials together, it will create a one junction and that will be a permanent junctions will be there. After that, no junction will be created. And if you want to expand the junction, you need to apply a certain voltage from outsource. Outsource means a battery you need to connect such that these electrons will get extra voltage to break this region and then come and join over here. Is it clear, all of you? But if you don't apply any external voltage, what happens? The junction will remain same. This junction will create as it is.
Sir,
Yes.
once we connect external battery and expand the
Don't think
junction.
about in terms of external voltage. Now you think about when you don't apply any voltage.
Okay, sir.
That condition I will take it to you in the next slide. And that is what the forward bias and the reverse bias. Okay.
Okay, sir.
Clear this thing, all of you?
Sir, if
This is
we
the
apply
condition.
voltage, then does the previously settled electron move forward or not?
That's what I told you. Don't think in terms of voltage. Put it for a next slide to come. This situation, if you look at this symbol, look at this symbol. This is. See, when you don't connect any supply over here, there will always be a small junction in between. And why this junction happens at a 0 volt, and that is what I had explained you. Clear?
Yes.
Yes, sir.
Okay. Now coming to the point. So this is what I'll explain. The formation of the band. Okay, when they combines, they'll create a junction. And that junction, there are the four different names of that junction. We call it a space charge region. Why we call it a space charge region? Anyone? Why we call it a space charge region? Because now that junction don't have this extra electrons and extra holes. Okay, so what they have, just an space in between which separates the p type and separates the n type. These electrons cannot go over here and these holes cannot come over here because there is a junction in between. So they will make separation for a charge particles with using that space. That's why it was a space charge region. So can you able to comment on this? What actually this I can say then? If that region doesn't allow the electrons to recombine with the hole, what that region we call in terms of resistance? Can you tell me the answer? What actually the job of a resistance?
Sir, is it insulator because band between p type and n type increasing, so electron can't move, like, so
No.
it will be more resistant.
Okay. So you are not able to say the insulator because in a semiconductor you don't have insulator. Are you getting or not? Clear? Okay.
It will
So it's
be
gonna,
high resistor.
correct. Are you getting or not? The previous one who said answer as an insulator, I'm telling to that person. You cannot say you have an insulator in a semiconductor. Are you getting or not? If you want to comment, you can able to comment on a resistance. Okay, so in between the deflection region, we have high resistance. Now, such resistance cannot able to, what you call, break by a electron which is in the n type to move towards the p type material. And that's why another name we call as a barrier potential. Barrier is nothing but a kind of a wall that has been generated. Or we call it a built-in potential because the potential has been generated by itself. That's why we call it a built-in potential. Clear all of you? Till the thing is clear till this place. Now there are the two types of currents we have. One current we call as a diffusion current. As you know that previously we don't have a deflection region. So when the electrons recombines with the holes, they will allow a current to flow. And that current called as a diffusion current. And that diffusion current takes place due to the majority charge carrier. Because these electrons combines with the holes, then and only then the current flows. And the current flows, and that current we call as a diffusion current. Now, as we told that there are also a minority charge carriers, but they are very less. So in this region, let's suppose this one is a plus and minus, they will also recombine. Yes or no? As the majority charge carriers recombine, obviously the minority charge carriers also recombine. Yes or no?
Yes.
I didn't understand that. Can you repeat?
As the majority charge carriers recombines, there is also a possibility that minority charge carriers are also recombining. Yes or no?
Yes, sir.
But compared to 1000, 0.1 value is very small. It's the same thing over here. The minority charge carrier currents are in the microampere, and that current resists these electrons to combine here. Why? Because as you said that when this is the resistance which is resisting these electrons to recombine with this hole, that means there is a small amount of current should flow such that that electron should not be recombined with this. That means that current due to flow of minority charge carrier we call as a drift current. Remember. And the drift current is responsible to resist this electron to move it from a deflection and go it to the whole region. Clear all of you? So there are the two currents, diffusion and the drift. Diffusion always flows due to the majority and the drift always flows due to the minority charge carrier. Clear all of you?
Sir, in drift current definition, it will minority diffusion will become there.
So yeah, this one is wrong. Okay, now clear? This is wrong. It's a minority only.
Yes.
Okay. Now look at this diagram for 5 minutes and understand the thing. Okay. Look at this diagram for 5 minutes. Till then I'll be there. I'll be coming back within 5 minutes. Okay. Just have a look on this diagram and try to come with one conclusion point. So what is the observation we have done on this? What is the observation you had done?
Sir, the layer is decreasing between P diode and N diode.
Okay. So you can say that the junction has been decreases. Previously the junction we have and now the junction has been decreases. So how that is possible? Now coming to the part of a battery. Okay. Let us have okay. Let me take to the last screen. Okay. Let's suppose the junction has been, this is the P type, this is the N type. What do you have actually? When you connect battery with a negative terminal and battery with a positive terminal. Here we have a junction in which we have no extra electrons and no extra holes. That is, the acceptor and the donor ions are there. Due to the negative charge, what happens? It will give a negative electron. Okay, so what happens? It will give the negative electrons. So what happens? This negative electron, what is sitting over here, they will get a more energy to recombine with these holes which is over here, and this is the positive part. We have an extra holes. When it enters the p-type material, this holes will get try to recombine over here. Are you getting or not? So what happens? This region will get narrower because each and every electrons and the holes have that much of energy can able to pass it from the junction and receive to the n-type material. Okay, so that is nothing but it was a forward bias. When you change the polarity, the p-type material and the n-type material, the p-type material has a negative polarity and the n-type is a positive polarity. So this positive terminal, what happens? The electron which is have an extra, the free electrons, will move over here. Instead of going this direction, it will move in this direction. Why? Because this positive charge, what you had applied for a battery, this positive, will attract the electrons on this direction, and this negative charge will attract the hole in this direction. So what happens? The deflection region, the previously was like this. Now this holes already is moving in this direction and this direction. The deflection regions get wider. More the voltage you apply, more the wider you will get. At one point, when you apply more voltage, the diode breakdowns and it will be like it will damage your diode yourself. So it is one condition when the deflection region reaches to this place, the આખે આખું સેમિકન્ડક્ટરમાં reverse bias થઈ જાય જંક્શન થી અને પછી તમે જે વોલ્ટેજ આપો, after that if you give a minor voltage, diode burn out, and that voltage we call as a breakdown voltage. Are you getting or not? Okay, we get more clear once you watch these videos also. Okay.
Semiconductors are materials that can
Voice is audible, all of you?
than insulators like plastics, but smaller curves than conductors like
Voice is audible?
They have very
Yes, sir.
Yes,
Okay.
sir.
properties which make them perfect for low power devices like computer chips. For example, the current that goes through them can be increased and decreased very easily, which makes them very useful in various applications. They are sort of like conductors, but not exactly. They're semiconductors. Now, silicon is the most commonly used semiconductor material, and it's also the second most common element in the Earth's crust. It's found in and harvested from sand, but it's also in rocks and can even be grown in a lab. The silicon atom has 4 valence electrons, and the silicon crystal is made up of cubes that have this weird shape. Now, I cannot draw that, so for the sake of convenience, I will use a 2-dimensional grid to represent the structure of the silicon crystal. Here we have a silicon crystal. If energy is added, for example, a photon can hit a silicon electron, the electron may get enough energy to break its bonds and actually leave the atom completely. In the bond where the electron used to be, there is now an empty space. That spot on the silicon atom now has a positive charge, and other electrons are attracted to it. Every time an electron leaves its spot to fill the empty space, it itself leaves an empty space back where it was before. If we apply a charge, we can see that although all electrons are attracted to the positive, only the ones by the hole can move closer. And so, although we obviously see that it is the electrons that are moving, it's much easier to think of a hole as a carrier of positive charge, rather than keep track of billions of electrons as they move around for a bunch of empty spaces. And so, although a hole is just empty space, we treat it like its own particle. It has no mass because it's just the absence of an electron, and we talk about it like a positive charge carrier, and of course it occupies space inside the crystal. In a crystal of pure silicon, there is an equal amount of both holes and free electrons. But if we add other atoms to the crystal, we can change the amounts of both holes and free. A common element we add to silicon is boron. Unlike silicon, boron only has 3 valence electrons. This is enough to fit into the crystal structure and bond with 3 silicon atoms. The covalent bond with the 4th silicon atom consists of a silicon electron and a hole, because boron just doesn't have another valence electron to put there. And so, by doping the silicon crystal with boron, we have added a hole, a positive charge carrier, without adding any electrons. Another common dopant for silicon is the element phosphorus. Unlike silicon, phosphorus has 5 valence electrons. Just like boron, phosphorus fits into the silicon crystal. This time, though, the phosphorus bonds with all 4 silicon atoms around it and still has 1 valence electron left over. This electron is not bonded and only needs a little bit of energy to leave the phosphorus atom altogether. So, by doping the silicon crystal with boron, we added an extra positive charge carrier, a hole. And by doping the silicon crystal with phosphorus, we added an extra negative charge carrier, an electron. Silicon crystals with extra holes are called p-type silicon, P for positive, and silicon crystals with extra electrons are called n-type, N for negative. Now, this is extremely important for you to understand. Even though there are extra holes and extra electrons, the p-type and n-type crystals overall have neutral charges. In terms of the crystal, the phosphorus electron is free because it doesn't fit into the crystal structure, and the boron hole is free because it opens a space in the crystal structure. But in terms of the individual atoms, the crystal has a neutral charge. Boron has less electrons than silicon, but also less protons, so overall the atom has a neutral charge. And phosphorus has more electrons than silicon, but also more protons, so it balances out too. And you might be asking yourself right now, so what? Why is this important? Okay, I'll tell you. P-type and N-type doping have various practical applications, but one of the most basic and common ones is the PN junction, which is found in pretty much every modern electronic device, including whatever you're watching this video on. I'll try to give you a basic conceptual understanding. Now, its name already tells you the basic idea of a PN junction. It is the junction between a p-type and an n-type semiconductor. Let's use the example of silicon once again, because after all, it's currently the most commonly used semiconductor material. So imagine that you have a p-type crystal doped with boron with extra positively charged holes on one side and an n-type crystal doped with phosphorus with extra negatively charged electrons on the other side. And you basically just put one by the other so that they touch. And what happens? Remember, both crystals are neutral, but they simply have freely moving negative electrons and positive poles. At the border between p-type and n-type, the extra electrons from the n-type silicon jump over into the holes in the p-type silicon and fill those holes. Because of this, a depletion region forms and creates a barrier between the two crystals. There is a layer of p-type silicon that now has extra electrons filling its holes. Remember, this area used to be neutrally charged. Now the electrons make this area have a negative charge. On the other side, a layer of n-type silicon just had its electrons leave. Remember, this also used to be neutrally charged. Now the lack of electrons makes this area have a positive charge. The layer of atoms at the border is now ionized and is depleted of charge carriers. This prevents any current from flowing. You can see why the PN junction is useful when we attach it to a circuit. Alright, let's put the negative side on the left and the positive side on the right. The negative side adds electrons to the p-type silicon. These first electrons want to cross the depletion region, but they're repelled by the extra electrons already there. They stop and then they drop into the holes created by boron and cancel them out. The boron atoms become negatively charged because of the extra electrons. This widens the depletion region and repels even more electrons, completely stopping any current from flowing. On the other side, positive holes are added to n-type silicon. Just like the electrons, the holes want to cross the barrier, but are repelled by the positive side of the depletion region. They stop, replace the electrons, and make these atoms positively charged. This widens the depletion region and repels even more holes, completely stopping any current from flowing. Alright, so that obviously didn't work. There wasn't any current. Okay, how about we try flipping the circuit? We'll attach the positive side to the p-type silicon and the negative side to the n-type silicon. This time the negative side adds electrons to the n-type silicon. The n-type silicon now has a massive excess of electrons, which are all attracted to the massive number of holes in the depletion region. So they come to those holes, they drop down into them, and they cancel them out. The depletion region gets smaller and might almost disappear if there are enough electrons coming through at once. Meanwhile, the positive side adds holes to the p-type silicon. The p-type crystal now has a massive excess of holes, which are all attracted to the massive number of electrons in the depletion region. So the extra holes come to the electrons, and the electrons hop over from their previously neutral atoms to the extra positive holes and cancel them out instead. The electrons are sucked out, the depletion region gets smaller and might almost disappear with a large current. So we see that in a PN junction, electric current flows in one direction but doesn't flow in the other. The PN junction creates a diode, a device which only allows the current to flow in one direction. These are very useful in turning alternating current that goes back and forth into direct current that only goes in one direction and powers all of our electronics. The PN junction is also a key element of logic circuits in all our computers, phones, calculators, digital watches, TVs, you name it. Essentially, the age of technology is powered by semiconductors, holes, doping, and PN junction diodes. Alright, that's it for today. Thank you very much for watching, and I truly hope you enjoyed this video and learned some new and interesting concepts and ideas that you can apply to your life in the near future. Goodbye and have fun.
Okay. Clear the things? Clear the forward bias and the reverse bias, all of you? Any doubt? Am I audible, all of you?
Yes, sir.
Yes, sir.
Any
Yes,
doubt?
sir.
No, sir.
No, sir.
Okay, fine. Now, so when the P type is connected to the positive and the N type should connect to the negative, it works as a forward bias. And when we have the reverse, P should connect with the negative terminal of the battery and the positive terminal N type, it works as a reverse bias. Now what you need to do, you have to draw a characteristics of a forward bias and the reverse bias. For that, I am sending the link to all the students. Those students have a laptop, they don't have a laptop. All the students can go to this link and can able to perform the experiment on that link. Wait, not that link, sorry. This is a BJT. Okay, go to this link. Next link, experiment 5. Go to that link and go to the forward bias. On sharing my screen, okay. What do you need to do? Go to that link, go to the forward bias, you get this screen. Here, choose for diode. I1N4001 is nothing but a different values of a diode. Okay, in the market, the device are known by their name. Different manufacturing companies have the different names. So here, National Semiconductor, N stands for National Semiconductor, makes this device. So the 4001, this VF is nothing but a cutoff voltage. Okay. Now what you are able to do here, the DC voltage and the resistance. Put resistance as a 1 kilo, that is 1000 as a fix. Put 1000 value of a resistance. Okay, it's okay, 1009, it's okay. And then what you can do, take the reading from 0 to 1 volt with a step of 0.1. So first take the reading at 0.2, then 0.4, 0.6, 0.8, 1 and 1.2. Let's suppose 0.2, this is the voltage. I didn't get any current and I didn't get any voltage across the diode. No current is flowing inside the circuit. What I will do here, at a 0 volt, no current. Increase the voltage 0.4. Add the float. Point 0.6, the resistance should be 1000 and 0.2, 0.4 let's suppose. Still I didn't get any current, put it over here. At what voltage you are getting a current, that is what you need to find. Here see the 0.6, till 0.6 you will not get a current. See here, 0.6 the volt current inside the circuit and the current voltage across the diode is 0. If you just increase to the 0.6 to 0.7, see here, a current and the voltage, you got it. This is what you need to observe. Okay, so at the table, go on increasing 0. With a difference of 5. Okay, like 0, 0 0.5, 0, 1, 1.5, 2, 2.5, till what voltage is there? It's still 4, 5 volt is there. So take a reading, then I will tell you. I'll ask anyone to share the screen. Okay, so I'm clearing all the things. You perform the experiment. Then I'll ask anyone to share the screen. Then I will tell you how to plot the graph. Because these are the things you need to put it into a lab 1 session. Okay. So all of you, once you've done the reading, raise your hand so that I can able to know that how many students had completed. And I will ask anyone to share the screen. Take the reading in terms of 0 to 5 volt with a step of 0.5.
Hello, sir.
Yes.
I cannot able to open a link. There is an error showing 502.
502.
Sir, me too.
Sir, me too.
I
My
can't
link is
open
Sir,
not
it.
me
opening.
too.
Sir, way too.
Wait. Let me. Now go to this link and open it. Still you are getting an error. Error. Still hit.
No, sir, it's just loading and
Sir, it's not opening.
sir, it's just
It's
loading.
also see error, sir.
Same.
Permits. Huh? Same.
It's not showing error, but it's not opening either. Like it's just loading.
Rest of the things are common. The things are also common. This is
Sir, in
theory.
my
In the theory, you go above. There is a procedure and the simulation. Go to the simulation. Okay. Jayes. જયેશ ને ઓપન થઈ ગઈ બાકી બધાને કેમ ઓપન નથી શેર કરો સ્ક્રીન જેમ નથી થતી
સર મારે ઓપન થઈ ગઈ મેં રીડિંગ્સ લીધા
Okay, not opening sir. Asta, share the screen. Let's see what error is coming.
Can I share screen, sir?
Yes, you can. Go to the chat box.
Sir, this same thing is
Google
happening.
Chrome up. Huh?
This same thing is happening in us.
Okay.
Yeah. Yes, sir.
Half of the students the same problem. Okay, go to this link. Might be this will open. Change it to the desktop mode in your Chrome in your mobile if you're opening. Then might you not get error. Change it to the desktop site.
No, sir, it's not opening, just loading.
Yes, forward was this opens. Okay, anyone just share the screen of a multi-sim? Anyone just share the screen of multi-sim?
Sir, I can share the screen of my mobile. It is working on my mobile.
Okay, Agnes working.
Sir, so I means
Wait.
Sir, I can. Hello, sir.
Okay, so we are telling, yes, you can present the multi-sim. Anyone?
Sir, I open without multi. Can I share my screen?
Yes, you can share your screen. Yes, Ankur. Okay. So, okay, it's opening. Why many students have the problem, I don't know. But it's
First of all,
opening.
then error so go to the desktop side and try.
Yes, that's what I told you. Go to the desktop side, then try. Okay.
Sir, can I
Once,
share my screen?
yes, you can share your screen. Anyone just present it fast. Okay. Did you get the table? Good. Go to the plot now. See, there is a thing, plot. Below the add to the table, there is a plot. On that voltage and all the things. Plot. Add to the table, plot and clear. Control લખ્યું ને જો forward bar circuit ની બાજુમાં right hand side corner. Add to the table and then plot. Readings બધા table માં તું add કરસ ને એની બાજુમાં plot લખેલું. Yes. એની બાજુમાં જો plot લખેલું. Yes. Go down. This is what the diagram. See here. This is directly, according to your table, you will get reading. So this is the graph you should get. Okay. Good, Yatnesh. Very good. Okay. So now anyone can have a multi-sim so that I can able to guide them. Okay, same way, you can go with the simulation with a germanium forward bias. Okay, diode made up of a germanium. So you should get the answer that what is the changes you are getting. Tell me the reason, what is the changes you are getting? Yes.
Hello, sir. Can I
Yes,
share my
sir.
screen for germanium
Yes.
diode?
Yes. I want to know what is the cutoff voltage for germanium, the forward cutoff voltage, after which the current start flowing. One kilo ohm, put it 1 kilo ohm. It's in the kilo ohm, so in the previous we put as 1,000. Now the 1 kilo ohm, okay. Now go on increasing. Don't go to the directly 1.15. See, point from where you get it the current, that is what you need to observe. Point 3. From the point 3 itself. Hmm. See, on that table till point 6 there is no current, but here at exactly at the point 3 you are getting the voltage. So that should be the cutoff voltage. Take few readings and then you can go with the plot. Okay. See here, the difference between the previous float and this float, that the silicon can able to give the more current after the point 6 and here it's giving you after the point 3. Very good, Yagnesh. Good job. Very good. Okay, now you can stop sharing the screen. This is what we need to understand. Now everyone just want to another things to be explained. I need a reverse bias to find the breakdown voltage. No need to share the screen. All the students write down after what voltage you will get the maximum current and find out the breakdown voltage for silicon and germanium for the reverse bias silicon diode, reverse bias germanium diode, and write down the answer in the chat box. Let us see how many students are writing correct answer. You can directly write down the answers. Okay. Ram, I am asking about the reverse breakdown voltage. For the silicon and the germanium, both are getting the same voltage.
Yes, sir. Nearly same.
Okay, same. The 30 volt is the correct answer. Okay, so this is how we can able to perform the practical. The same thing you can also do it into a multisim also. Okay, connect the same circuit with the multisim. So let me show you from where you can able to take diode and all the things, so that the students who have the multisim can able to do it directly from there itself. So I'm sharing the screen of a multisim. Okay. Okay. The screen is visible?
Yes,
Yes,
sir.
sir.
Okay. So
Yes,
what is
sir.
able to
Yes,
do?
sir.
Take a one diode, 1N4001, put it here. I need one resistor. You can directly take it from here. Place source, DC power battery I need. I'll put it over here. I need one ground. I'll put it over here. And one resistor I want. So here, take 1 kilo ohm resistor and put it here. Connect all the components together. Rotate this diode. Okay. Take one multimeter. Connect here. Take a multimeter and connect here. You need to measure a voltage across the diode. That you want to measure a voltage DC. Then measure a current because it's a single loop, so current will be same in the whole loop. I want to measure a current DC, place it here. This will give the current, this will give the voltage. Start from here, let's say like a 0.1. Start simulation. At 0.1, look at this, and nanoampere millivolt. Stop the point 2, simulate. Still the current not in ampere we have. Now voltage across the diode is still not 0.7, so the 0.3 microampere, 0.4 increase again the microampere. Directly it will change from micro to milli. 0.5 still micro. We put it at 0.6 still micro. When you put it as a 0.65, so it's in microampere. So when you put it at 0.7, it is not cutoff voltage. Now 0.8. Now increasing the graph. 0.9. Okay, due to this high resistance. Okay, understood. It's okay, but 1000 is also good. 0.9, 1 volt, micro, 1.5. Current is increasing sharply. Okay, previously it's like a very small, and now it starts increasing like small voltage changes, it will increase more. So 1.6 milliampere, small, just a 0.1 voltage makes a 2 difference. Okay, when you plot the graph, you will get a more idea. So for you, I will teach these things in the next class, but for you, I am just loading this. I need a DC analysis starting from 0 to 1 with a step of 0.01. I have to measure the current and simulate. See, this is the graph. Same graph what you are getting. Okay. So I'll teach you this how to get a characteristics in a multisim, and I'll teach you that we have a online multisim also. Like same circuit you can able to implement in an online multisim. Online NI we have National Instrument. No. Online multisims. This one is a live multisim circuit simulator. Okay, so I already have the account. Directly I can go to the create circuit. It's a multisim.com create. That is an application. It's saying those who don't have the laptops can able to do the circuits on online also. Okay. Here there's a symmetric grapher and a splitter. When you put a splitter, on this side you can able to draw the circuit, on this side you can get a graph. Okay. Here so many things are there, like the DC battery. If you want a diode, you can take the diode and put it here. If you want a resistor, take a resistor and put it here. If you need a ground, take and put it over here. And then connect with this wire. Connect with this wires. So this is also one good tool to use. For those who don't have a laptop, they need to perform the experiment on the online. So once you do that, Everything I will teach you in the next class. Okay, but these are the things are there. Is it clear, all of you? Till the today's session, is it clear? I hope there is no
Yes.
doubt for the session. Lab zero, nothing all. Okay. Okay. Line by line, all the students write down the attendance in a sequence. Those who write can leave. Those who wrote can leave. The first one. While the frequency is low, the time is very high.
Excuse me, sir.
Yes.
Sir, still I can't receive your email.
Only Janil is the one.
Yes, Janil Shah.
Alright, Sandy, did your Marwari education mail ID is working?
Sorry, I can't understand.
Your Marwari University mail ID is working?
Yes, working.
You should get the mail. I don't know why it's not getting. I send you the
जी सर,
request also.
उसमें दूसरे फैकल्टीज के भी मेल आए हुए हैं तो वो वर्क कर रहा है.
Hello, sir.
Yes.
Sir, actually, I was facing connectivity issues. That's why I wrote my attendance last.
Okay, fine.
Yeah. Sorry, sir.
It's okay. January,
Yes, sir.
no, wait, just a wait. Janil saw the same. Check your Marwari University mail ID, whether it's correct or not.
Just a minute. It's janil.shah111292@marwaduniversity.ac.in.
Now check.
Yes, sir. It's received. Thank you, sir.
Okay.
હેલો સર.
Yes.
સર હું પરમ બોલું, કાલ ફોન કર્યો હતો ને. તમે લેપટોપ લેવાનું કીધું હતું ને, એમાં પ્રોસેસર કયું લેવાનું?
અત્યારે લેટેસ્ટ 4 i5 છે.
દુકાનવાળે પૂછ્યું કે કયું પ્રોસેસર હોય એમાં.
તો વાઈફાઈ ચાલે છે અત્યારે, એ જઈ શકે.
ઓકે, થેન્ક યુ સર.
હા.